And thank you, Alan, for inviting me to give this keynote. It's going to be a personal perspective based on all that experience that Alan's just told you about, from working on a cobalt plant to working in industrial R&D, academic R&D, engineering companies, designing processes, right through from the beaker scale right through to the actual process being built and operating. So I'm trying to combine all of that into this personal perspective of what I think is going to happen to the future of cobalt, nickel, copper processing in the age of lithium-ion batteries. So let's get on with it. The age of lithium-ion batteries, it's not been with us long, but it's had a very, very profound effect since their introduction in the early 1990s to our way of living. We've all got, I think, one of those. Probably everybody in this room's got one of those. Most people will have one of those. Many of you will have laptop computers with you. Some of you listening to me speaking now will receive a call and have to go out and take it. Some of you will be checking your email and messages. Some of you will be following this presentation on a tablet or a laptop. And it's widely believed that lithium-ion batteries are going to be the basis of the upcoming electric vehicle revolution that we all anticipate is going to happen. So the age of lithium-ion batteries. The term battery is attributed to Benjamin Franklin back in 1748, when he wasn't being a founding father of the United States, and God knows what he thinks of number 45. He was a very accomplished physicist with a particular interest in electricity. And he observed a bank of what were called Leyden jars, which was probably the first type of electric capacitor that was developed. And he said, this looks like a battery of Cannon. And the term apparently has developed and stuck since then. The first battery as we know it today was developed by Alessandro Volta in 1799. It's called the voltaic pile, and it's people will, high school teachers, one of the things that it's beloved of, and it developed from the voltaic pile to the Daniell cell and the Leclanche cell, and I think many of us will probably remember playing with those in high school. This is a surprise to me. The first rechargeable battery, the NiCad, was developed in 1899. I didn't realize they'd been around that long, so I was a little bit surprised to find that out. David just referred to the fact that lithium-ion batteries have been here since 1974. From the information I have, the first relevant patent was issued in 1982, and the first commercial lithium ion battery in a piece of equipment was the Sony mobile phone, which came in the early 1990s. So the age of lithium-ion batteries as we know it is less than 30 years old. I'm just going to do a little bit of a sort of a history here to try and put everything into context, because we're talking about lithium-ion batteries in electric vehicles. So the internal combustion engine was developed in 1859 by Etienne Lenoir in France, and that's what it looked like. And the first motor car is generally regarded as having been developed in 1886 by Carl Benz of Mercedes-Benz fame. So the rise of the motor vehicle is something that's quite interesting. This is a picture of New York, Central Fifth Avenue in New York in 1900. Not a sign of a motor car anywhere around, even though it was invented 14 years previously. Just over a decade later, there's the same thoroughfare, not a sign of a horse anywhere. So in the matter of a decade, the rise of the motor car replaced horse-drawn buggies, particularly in the States. The development of this was a little slower in Europe, but it really took off because of the advent of the Model T Ford, which was the world's first mass-produced car. And the main incentive then, as it is now, was environmental, because horses apparently deposited over 1,000 tons of manure on the streets of New York every day. Quite a clear-up effect, and it must have been a wonderful place environmentally. The atmosphere, I think, would have not been conducive to making love, for certainly. So, will electric vehicle growth be as quick as it was for the motor car? Are we going to replace this with this? And if so, how quickly? And to what extent? And what are going to be the restraints that prevent us from doing so? It's interesting that the motor car and the electric vehicle are both dependent upon a single material. The car is dependent upon oil, and the electric vehicle, as the technology exists right now, is going to be dependent on cobalt. Oil is abundant. Cobalt is geographically restrained, as we've just heard from David. There are many locations around the world where you can find oil. With cobalt, as we've heard, 60% is in the DRC. Oil is a primary product, and cobalt is a byproduct. Oil is easily refined to petrol or gasoline, whichever your language is. Cobalt has very, very complex chemistry, as we will see as I go through this presentation. The lithium-ion battery. And this is from what I've read in the literature. I'm by no means an electrochemist, and this is supposed to be a very, very simplistic representation of what a lithium-ion battery is. That diagram is in the paper, and it's probably easier for you to read it there. But lithium-ion batteries work on a principle that's called intercalation. A cobalt oxide structure is developed, which is a layered structure. So you have in the cathode and the anode, they have to have a layered structure, and the lithium ions are able then to swim through the electrolyte from the anode to the cathode. When the battery is totally discharged, all the lithium is with the cathode. When it's fully powered up, then the lithium is with the anode. So the cobalt structure can tolerate virtually 60% of the lithium that's in it can depart from the cathode and go to the anode. This is much higher than it is for, say, a similar manganese or nickel structure. But nevertheless, as we know that because of the various types of batteries that are around, that you can substitute some of the cobalt with nickel and with manganese. But the information that Argonne National Lab in the States publishes, that they reckon that the very minimum you have to have 10% of cobalt in that structure with the way that batteries are at the moment. So that's the minimum that you have to have there, and future batteries will have to have that, at least that amount in. So cobalt is not going to go away. It's going to be absolutely necessary as we move forward into this revolution. I've just summarized here a few types of lithium-ion batteries. What we need to work out is that the LCOs are what we find in our phones and laptop computers and tablets. NMCs and NCAs are the ones that are going to be appearing in the electric vehicles as they move forward. Those seem to be the favored ones, and the reasons, some of the reasons I put here. There are more reasons outlined in the actual paper that's in the proceedings. I'm just going to repeat here a little bit of what David Waite showed. So as we move through time, then in the first decade after cobalt lithium-ion batteries were on the market, we saw a relatively small use of cobalt in lithium-ion batteries. As we moved through the next decade, then that amount increased quite considerably, and in the future we're going to expect it to be even more. So as I say, cobalt is not going to go away. It's going to be an important, and lithium-ion batteries are going to continue to be a major consumer of cobalt as we move forward. I'll just briefly touch on these, but as Tesla has developed its batteries, the best projection we can get from them is that there will be about, the lowest you can go will be about 4.5 kilos of cobalt per car. At the moment, there's typically 10 or even 15 kilos of cobalt in a car. So the hope is that, at least Tesla's hope is that you can reduce cobalt usage to 4.5 kilos. I know that Elon Musk has gone public and saying that he's going to have batteries that have no cobalt, but I don't think that that's going to be viable at all. BMW, on the other hand, optimistically hope that they're going to get what's called solid-state batteries. I guess something along the lines of the solid-state hard drives we have in our computers. Let's hope that the solid-state batteries are going to be a little bit more reliable than the hard drives that I've experienced anyway. The golden fleece of batteries then is the solid-state battery. That is really what the battery manufacturers that I've talked to are trying to achieve. That type of battery is safer. There's no volatile organic electrolyte. There's therefore minimal risk of fire taking place. They have more than double the capacity for going on a trip. So instead of going typically 300 kilometers, which a car can do today, Volkswagen in particular hopes that they can get 750 kilometers on a single charge. For me, where I live, then that's traveling from Montreal to Toronto on one charge, and that you've no idea how great that would be if I could get from one major Canadian city to another Canadian city without having to plug the car in. Solid-state batteries will have a higher energy density, which of course is why they'll be able to go further. And they'll be smaller and more compact. But opinion is very, very strongly divided as to whether these solid-state batteries can be cobalt-free. And there's no consensus of opinion anywhere that I can find anyway, whether we can make batteries that don't have cobalt in. So I think cobalt, as I say, cobalt is here to stay, and David will be very happy about that. At the beginning of the age of lithium-ion batteries, 1990, David's predecessor gave a presentation which was very interesting. A decade prior to 1990, at the end of the 70s and the early 80s, cobalt price had a similar spike like that, which we've had just recently, but there was a similar spike at that time when cobalt went to $30 a pound. That promoted what was called a cobalt rush. And I just joined Noranda at that time, and because I'd worked on a cobalt plant, I was told, develop a process for the Blackbird cobalt deposit in Idaho. So we did it. We developed a process, and I'll talk a little bit more about that a little bit later. That was driven by fears of cobalt shortages because of the burgeoning superalloys market at that time. It was also exacerbated by rebel incursions into the plants in the DRC, with soldiers coming down from Rwanda and Burundi, as they still do. And they were taking over these plants, and a number of operators were in fact killed. So that also gave the impression that there was going to be a severe cobalt shortage coming out of the main supply line in the Congo. But as always, and as has happened again recently, the panic has receded, and cobalt prices is come back down to more realistic and typical levels that have been that it's been at traditionally. So, as I said, the Cobalt Institute gave a presentation in 1990. In that presentation, he noted that the production of cobalt was 24,000 tons, i.e. about 1/5 of what it is now. that the identified global reserves were 2.4 million tons, so that there was ideally 100 years of supply left. So the conclusion was that cobalt was not in any particular danger of running out. 60% of cobalt production at that time was from Zaire, which is what the DRC was called then. So the ratio from the African copper belt countries at that time was 60% came from the Congo and 40% came from Zambia. I was reading through ALTA 2000 proceedings, Alan, and I noticed a paper there, and there was a very interesting quotation there, and it said that it was talking about laterite projects, and as many of you who've been involved in the engineering cost estimates from laterite projects, you will see that byproduct credits are always a big thing. And most of these laterite projects, to be deemed economically viable, they needed a cobalt credit. So it was said that laterite projects that are overtly dependent on cobalt credits to enhance their viability may not prove to be viable. Of course, lithium-ion batteries hadn't been thought about then. And so the quote went on and said, in response to low cobalt prices, demand must be stimulated and new uses for the metal need to be found. Who would have known, hey? Totally unknown that lithium-ion batteries were going to be there, that cobalt was going to be, this new use for cobalt was going to come on the scene. So I thought that was kind of ironic to find that quote less than 30 years ago. In David's presentation, he mentioned taking numbers from the United States Geological Survey. I've done the same. So the most recent production figures from the USGS shows that annual production of cobalt is 110,000 tons. There are 7.1 million tons of identified reserves. So if you divide one by the other, there's enough identified cobalt in the world to last for another 64 years at present production rates. Now, we've heard that the production rates might double or triple. So you can see that the amount of cobalt that is identified on land-based reserves is not going to last very long. It's certainly not going to see the electric car revolution through to the end. Nickel, production 2.1 million tons, reserves 74 million tons. So on that basis, we have 35 years of reserves left. Copper, 19.7 million tons, identified reserves 790 million tons. That's also going to last about 30 years. Now, copper's an interesting one because I'll get to that in a minute. So in 1990, there was 100 years of cobalt left. Despite more cobalt being identified and despite more cobalt being used, 30 years later, there is just under 70 years of reserves left. But the result, what is interesting is that the production ratio from Zaire to Zambia, or DRC to Zambia, is now 30 to 1. So Zambia has sort of almost disappeared off the cobalt map. It's not like it used to be, certainly not when I was there. So the DRC is a lot more dominant than it was then. But of the three metals, copper is the one that's has got the most problems. And nickel is also facing similar shortages to copper, and I'll come on to that in a minute. Potential Chinese dominance of the nickel and cobalt market, especially a company called Tsingshan, which is just taking over part of Indonesia right now. That's going to happen, and we have to be prepared that there's going to be a major Chinese input and takeover of these markets. Now, it's what I was referring to. Copper is in big problems because if the chief executive of Anglo reckons that if there's 2% growth of copper per annum every year up to 2030, then we need another 13 Collahuasi copper mines. And Collahuasi produces over half a million tons of copper a year. So that is not, I don't think that's going to happen, because no such mines are on the horizon. Even though Ivanhoe is doing a lot of work in the DRC, and I noticed just the other day that Ivanhoe has now gotten into bed with Chinese concerns, so China is taking over that one as well. Nickel reserves are approximately 70% laterites and 30% sulfides. Despite the modest, and I use the word modest there advisedly, successes of HPAL at Coral Bay, at Moa Bay and Batavia, I think HPAL, we would all agree, and we certainly, that was the case at the Alan Short course at the weekend. HPAL has had a very checkered history. It's got many equipment failures and some massive cost overruns. It's highly capital intensive, and experience suggests a very, very long ramp-up time. As I said, Xinjiang is taking over Indonesia. They've acquired the Weda Bay project from Eramet. They're going to make, Weda Bay is going to become an NPI project, but they're also announced that they are going to build the fastest and cheapest HPAL plant. We shall see that if it happens. I think the industry should just drop HPAL, and I think it should investigate things like chloride as a processing route, because I think it's much more efficient. And as we'll see, the world's major nickel cobalt refineries are chloride based, so it would kind of make sense to have a chloride up front as well. So I'm just going to go through this one quickly. It's just reiterating what I've already said, that production and reserves are dominated by DRC. The focus is on cobalt because of lithium-ion batteries. If we do a quick calculation here, in 2016 there were about 2 million electric vehicles in total. Compare that to every year, there are 70 million new motor cars produced. So if we take the Tesla very optimistic estimate of 4.5 kilos and the generally accepted 30% of the personal vehicle market being electric vehicles by 2030, then the increased cobalt production on that basis has to be 90,000 tons. So that's more or less the same as current production. So that sense, current production has got to double. And this is very similar to the estimate that David showed. This is exactly the same graph because he sent it to me. But my quick calculation above there shows that if you extrapolate this Morgan Stanley thing to 2030, then we will get the same estimate that I've got. On the other hand, the Commodities Research Unit did a study for Anglo-American, and they suggest that it's going to be a threefold increase. So somewhere between double and triple is going to be the increase in the usage of cobalt over the next decade. So what are the options for increased cobalt production? Because that's really what we've got to think about. We can increase production from current operations. Glencore is aiming to double production in the DRC, and I wish it good luck. Ramu has announced it's going to double production. Vale has indicated it's going to spend an additional 500 million on Goro, despite the fact that it's just losing money hand over fist. It's going to be it's kind of I think it's a political metallurgy decision, just to stay in business. Vale is also going to increase production at Voisey's Bay it's investing another 2 billion in the mine. Meta in Turkey has indicated that it's going to quadruple production, and it's going to couple this with a 25 megawatt battery plant. Talking now about new old mines. These are mines that used to exist but closed down many years ago. But with modern processing methods, they are now going to become, again, we hope, viable operations. We're going to hear at this conference about Clean Tech Sunrise project, which used to be called Cyaston. The Idaho Cobalt in the US, Cobalt Belt in the US, which is where the Blackbird project that I worked on many years ago was situated, that's receiving a lot of renewed interest. E-Cobalt Solutions is a small company. They're aiming to produce 1,600 tons of cobalt in concentrate. They're estimating that in 2020. Whether that happens is very much open to doubt. And the Ontario Cobalt Belt, centered around the aptly named town of Cobalt, is receiving an awful lot of attention. There are at least 5 junior mining companies there exploring. Interestingly, the mines in that belt, despite the name of the town being Cobalt, it was always mined for silver. Cobalt was just a nuisance byproduct. And the last mine shut down in the mid-1980s. The Copper Belt, where I started my career, where David started his career. Copper Belt slags, they're all over the place. In the early days of the Copper Belt, smelting was very inefficient. And the slag dumps can contain up to 3% cobalt, which would make them one of the richest mines in the richest cobalt mines in the world. A slag retreatment process was installed at Chambishi and in 2000 and shut down in 2010, mainly because of the low nickel prices and low cobalt prices at the time. The Belgian Forest Group is intending to retreat the slags from the early years of operation in the Congolese copper belt. Tailings, which is a big thing for me, I'm very, very keen on retreating tailings. The pyrrhotite tailings of Vale and Glencore, or as Inco and Falconbridge, as I kind of know them, in Sudbury in Ontario. These tailings that are they've been mined, they've been milled, and they've just been dumped. Contain up to 1.2% nickel and 0.03% cobalt. There's somewhere between $8 and $10 billion of value in those tailings. We've developed processes that can retreat those tailings. You can recover all the copper, all the nickel, all the cobalt, the PGMs. You can make a usable iron product, and you can recover electric power. You would think that the companies will be jumping at that, but no, these things are grandfathered, and because they've loaded with arsenic, nobody wants to touch them, because as soon as you start touching them, you develop an environmental liability. So we have to have some political metallurgy here to retreat these tailings, because they're just a source that cannot be avoided. I'm just going to do a little bit about the Congo. How am I doing for time, Alan? Oh. I won't do a bit about the Congo. As David said, it's an approximate size of Western Europe. It's very mineral rich, it's low GDP, one of the world's most corrupt countries, and there's no rail or road link from the capital, Kinshasa, which is over here, to the copper belt here. Significant lack of infrastructure, but DRC also faces many other issues that it will impact on its ability to meet demand. 20% of the cobalt is by artisanal mining. These miners get about $9 a day, which is absolutely essential for them to live on. Doesn't seem much to you and I, but it means it's the difference between life and death for them. But it's still exploitation. There's no question about that. And as David alluded to, we've got to find some way of dealing with that. Congo has many, many health issues which are not so they're not so obvious as the conflict mineral types of issues. Central Africa has the world's highest instance of AIDS. 60% of the male population has it. The outbreaks of Ebola are very common, and I was just reading in the paper on Friday, in fact, that the World Health Organization doctors who are there are leaving because the rebels are coming in and they're raiding the clinics, they're killing the nurses and the doctors. Just make any logical sense to me. Here you've got people trying to help people from dying, and ideologies force them out. Malaria is there. When I was in Zambia, malaria was to the far north of the Congo, and then the World Health Organization decided to stop spraying for DDT, and it's now it's not only all the way through Congo, it's all the way through Zambia, it's all the way through Zimbabwe, and it's even been found in the Kruger Park in the north of South Africa. Manganese nodules. I'm going to go through these very quickly. It's been you can see there that there's a huge amount of manganese, cobalt in these crusts and nodules on the seabed floor. And if we're going to have a cobalt-based economy, then we're going to have to mine those. The technology exists to mine them, but you can't. It's not something that you can do on a large scale. Sovereignty jurisdiction is obviously going to be a big issue, as are environmental issues. The International Seabed Authority is able to issue permits for mining, but how they're going to issue those, because we don't know what the environmental problems are going to be in terms of mining them, but we have to mine them eventually. I'm just going to go through these. I'm not even going to mention them. They're all in the... it would take 2 days of a short course to do all these circuits. And I was told when I first started my job in Zambia, I met the head of R&D from Utukumpu, and he said, if you want to drive somebody crazy, get them interested in cobalt chemistry. So I've been interested in cobalt chemistry, so I don't know whether I'm crazy or not. But the point I've put flow sheets for all of these in the write-up. As you can see, there's an awful lot, and I'm not going to go through them. But compared to copper or zinc or lead or any of the other major metals, they all have maybe one or maybe two methods of processing. Cobalt and nickel, that you can do it in chloride, you can do it in sulfate, you can do it in ammonia, you can do it in mixed chloride sulfate. You can either do it by pressure oxidation or pressure leaching or atmospheric leaching or ammonia leaching or heat leaching. So there is a large number of ways of refining cobalt, and that has an impact. Something I want to get to if I have a few minutes. I was going to make one point about the Blackbird project that I worked on. It's in Idaho. The processing flow sheet was very economical. It was about $2 a pound. And cobalt was $20 a pound at the time. So we thought, great, we've got a project here. What we didn't realize that the mining costs were $25 a pound. So there's always a reason in our industry why something hasn't been done that seems obvious, and you have to look for that reason. And that's a point I want to make, because I'll get there eventually. Sorry about all this. When I went through it myself, I didn't talk so much. So, lithium-ion battery recycling will become mandatory, and I think it has to be, because we're going to be a shortfall of cobalt, and you have to recover that cobalt and treat it and put it back into the economy. The estimates vary as to how batteries are currently collected and recycled. Significantly more effort needs to be devoted to their collection. It's estimated that about 100,000 tons of batteries were recycled in 2018. It's estimated that if we can recycle batteries as much as we possibly can, and it won't be electric vehicle batteries for the reasons that David outlined a few minutes ago, but it will be your laptop batteries, your cell phone batteries, things like that, that we can get up to about 40,000 tons of cobalt. That's not going to be enough. The Argonne lab in the States has made this statement, and they are investing $15 million into developing a process for the recovery of cobalt from these batteries. I think the battery process has to be what I call end-to-end. And that means that you have to separate and recover all of the components of the battery. That means the plastic and metallic linings, the anode material, graphite, cathode material, the connectors, and the electrolyte. The electrolyte is a very important component, and I put a graph in my paper that you can recover about 10 or 11% of the mass of the battery is electrolyte. You have to recover that. I think the management of recycling at the moment has been very poor. I would say it's been mismanaged. Spent batteries are inherently dangerous. We've had incidences of laptops catching fire on planes. We have the incident of the train explosion in Texas a few years ago. Spent batteries are going to be in various states of charge or discharge. We've taken batteries and you split it open and it catches fire immediately. So they are dangerous. The cobalt, nickel and manganese are generally in their higher oxidation states, so they're very, very reactive. Some of the cobalt might even be in its very rare +4, which is very unstable oxidation state. So I think reprocessing of these batteries is essential. It has to be done, but it needs a great care and attention to detail in the way you do it. So as I've said before, batteries are complex structures. The anode materials, graphite, the casings and connectors are plastics, steel, aluminium and copper. We need to recover those. Cathode material, of course, is various formulations, LCO, NMC, NCA, LMO. The electrolyte is an organic liquid, such as ethylene carbonate, so it's got a vapor pressure and it's flammable. And there's usually a lithium salt in there, lithium hexafluorophosphate. So the electrolyte itself is dangerous because this material is hygroscopic, so it absorbs moisture from the atmosphere. And lithium hexafluorophosphate reacts with water, gives off HF, so you have to be very careful of that when you're doing it. As I said, the organic is volatile. As such, therefore, lithium-ion batteries are not easy to process, and care and attention to detail is really needed. At the moment, the major way of doing it is incineration. You get various battery collectors collect the batteries. They might break them open, recover the plastics, but then the interesting material is usually sent to a smelter, which is mainly Umicore. And smelting is inherently inadequate, and it's inherently environmentally unfriendly. It recovers only the metals, and that way it only recovers them in an alloy. Plastics are incinerated and used as energy, which is going to create greenhouse gases and potential chlorinated hydrocarbons. It has a very high carbon footprint. The lithium is lost because it reports to the slag. I've seen a number of recyclers talking about hydrometallurgical techniques as though it's some sort of universal panacea for treating batteries. In fact, I noticed it from a statement from VW just last week. We are going to collect batteries and we're going to recover them by hydrometallurgical techniques, whatever they may be. I didn't go through the commercial operations, but cobalt-nickel separation is not easy, and that's why there are so many ways of doing it. Typically in commercial operations, the nickel to cobalt ratio will be 10 to 1 or greater, and processes have been developed for separating that way. But even if you get 811 NMC batteries, that's still more than 10% of the total battery mass being cobalt. And once you start getting higher cobalt levels, then the methods of separating cobalt from nickel become increasingly difficult. And I don't think all the wannabe recyclers who are out there really appreciate that. Quickly through existing processes, they're neither sustainable nor do they recover all the components. Smelting is the main process worldwide. It's unsound, it has a large carbon footprint, and I've just listed a few of them here. There's Umicore is the leader. It recovers nickel and cobalt only. Accusa in Finland is just a physical separation process, and the important stuff is sent to Umicore. Retrieve basically tries to repurpose the batteries, but that's a combo hydro-pyro process. Recupil is probably the most efficient of the processes, but I've read their patent and it doesn't make sense to me, because they say we're stabilizing the lithium hexafluorophosphate by adding chloride. But if you add chloride to cobalt-3 or nickel-3 or manganese dioxide, you get chlorine evolved, so the chloride can't stay there. And then they're going through an aqueous process, and then they're recovering the lithium lithium fluorophosphate as is, and because it reacts with water, I don't see how they can do that. So their process seems to be a little bit strange to me. There's a lot of new. Just 2 minutes. I'm almost done. We've got American manganese, which has just got a patent issued to it, and they are touting that patent on all the business shows. They're calling it a recycling process patent. What it actually does is they're crystallizing sodium sulfate and calcining it and saying that's how we control our water balance. So these type of little people, little companies, little juniors that do that really annoy me, and I think they do a great disservice to our industry. Life Cycle, which is close to where I live in Montreal, they're receiving an awful lot of attention on CBC News and the local newspapers. Well, actually, all they're doing is writing a blog saying we have to recycle lithium-ion batteries. Neometals is here. They've just filed for a provisional US patent. It's an SX-based process. When you dissolve the batteries up, you've got very high, and it's supposed to be a process that treats all batteries. But if you've got if you've got very concentrated solutions, then trying to separate cobalt, nickel, and manganese by SX is not a good idea, because you need constant feeds, and Cobalt SX is not designed for recovering cobalt from concentrated solutions. The Urban JV has filed PCT applications on five patents, which is covering all aspects of lithium-ion battery reprocessing, and I'm very hopeful that that's the one that will go forward. Typical cryogenic discharge curve. I'll get to the end. I put these down as a few points to talk about. Will there be an electric vehicle revolution? Well, yes, but not to the extent that's being called for. You can read that yourselves, actually. I think Alan wants me to finish here, so I'm going to just recycling is going to be it's going to become mandatory and something we've got to do. Finally, I like Calvin. I say, my ism is sort of optimism that our industry can overcome all these difficulties, but skepticism that the electric vehicle revolution is going to be what we all think it is. So sorry for taking so long. Hope it was clear, and thank you for listening.
We're going to leave questions so we can get a hold of later during the course. But of course, a very comprehensive paper which you all can read. For Bryn is written, and there's a lot more information there. We will be putting it up on our website, freely available, as we do all the keynotes after the event. So it'll be there for you, as will be the a video of his presentation. So let's just once more thanks Bryn very much.